What I want to talk about is the Parsl task model and how that relates to how I've seen various people trying to do MPI stuff in Parsl, which makes me a little bit uncomfortable. And this talk is basically the result of me thinking about that discomfort. So I'm going to talk about what the Parsl task model looks like, what the MPI task model looks like briefly. We've got 4 different implementations of MPI now, I think, in Parsl. And I'll briefly review how those, in my perception, do MPI. And then maybe some ideas for how we can, some of the things that I will say I dislike, maybe some ideas for how to make that a little bit nicer. So I'm going to start with what the task model looks like for workflow authors. So that's the traditional, what we would call a Parsl user. That's someone who's writing a workflow. They can define an app using this Python app decorator. They can invoke it. They can invoke it in quite complicated expressions. So that expression in the middle defines a 2-step workflow because it calls add twice. And at the end, you can wait for your result. And hopefully that result will pass 5, 6, 7, 8, 9. Yeah. Okay. So that's what a workflow looks like for workflow authors. That's how you submit a task. That's how you see the result. And onto those, I'll mention this now. I'm not really going to talk about this much, but it needs to be there in hanging around in the background the whole time. Onto a call of a Parsl app, you can give a resource specification, which at the moment is just a key, string key, any object value that is defined per executor. It's a very loose schema. So you can annotate with sort of a description of how an app should be run, not what should be run. And that's going to be hanging around like a ghost throughout the rest of the talk, but I won't really mention it explicitly again. So when a user makes this is going to go, makes a call like add. This is going to turn into basically a function call on the data flow kernel. That's sort of the core task management bit of Parsl. And it's going to turn into this submit call where we say, all right, the user wants to call this function. Here are the args. Here's some other options like caching and whatever. Here's the executor we want to run it on. And so this is sort of really a syntax translation from this function call syntax into something that looks like a submit call. And that turns into a task record, which started off as a dictionary, but now it's a bit more structured. And this task record structure says, here's the function we want to call. It's an add object. And here's the arguments, and here's the executor. If you look at the args, you'll see that we've got an explicit 3, but the second argument is the future from the first task. Then we might look at file staging. Nothing happens to do with file staging in this call, so I'll skip anything happening here. Then we do dependency resolution. When the first task's finished, we can now say, all right, we're going to modify the task record and have a different task description. And instead of that second future, we can now say, all right, we know the value is 6 because we run the task. We can do checkpointing, where we look at these arguments. We look at, say to the checkpoint DB, have you seen an invocation like this before? So the checkpoint DB will look at the function object that's being called and the arguments. Maybe it finds a match, in which case we can short circuit execution and say, I know the value right now, we don't need to do any more. That's usually not the case though, and we can move on to the next step. We stick an error wrapper object. So there's a lot of wrapping happens in Parsl. And this is the first bit here, is we replace the function, which used to be an add object. It's now a new function called wrap error, which inside its closure, it happens to have the reference to the add object. And if you've got monitoring turned on, we do the same thing here. We now stick a monitor function around everything. And so the function that the task record describes is now a monitor function, which will happen to call the wrap error function, which will happen to call add when you invoke it. And then we hand over all of this to your chosen executor. So this is where the point where we hand over to the code that interfaces to high throughput executor or radical pilot or flux or work queue or dragon. And that looks like this function call here. We call submit, we hand over the function, we hand over the resource spec, and we hand over the arguments and keyword args. Okay, so all we're handing over is a Python function, which is now quite complicated after all this elaboration. And we say, just run this function. You don't have to think about anything else. Just run this Python. That's all. Okay. Parsl also says it can run bash apps. And if you've looked at this API here on the previous slide, you'll see there's no way in here to specify a bash app. Okay, you can only specify a Python function, a Python app. So what we do is we've got this different syntax, bash app, and you return a string that's the command line you want to run. There's nothing here that looks like it's going to run the command line either, right? But this syntax, because we have a separate decorator, it sort of tricks people into thinking there's some strong notion of a bash task type that's distinct from the Python task type. But hopefully that earlier API stuff you've seen shows that there isn't some different task type, right? This is some magic that's happening. The magic that's happening is we just do another layer of wrapping. We have this remote bash executor object, which we then wrap around in here as well, which calls the user function, and then it just forks out. It does the equivalent of os.system, or it does a different call. But
yeah, Ben, can I take you back to the last slide? There was a part there.
yeah.
What do you mean by crossing the executor API boundary?
What I mean is this call here.
Is that the, oh, go ahead.
This is where we go from, this is a call that lives inside the DFK. So this is core Parsl code. And now we've got that task record, and we're going to say, all right, now I'm going to hand this over to some executor that's going to execute it for me. And this is basically the only API call that is available for doing that.
Okay, and you're saying that the concept of here,
look at this call. There is no Unix process call option in this API. You pass in a Python function, nothing else.
Well, okay, bringing forward that.
Yep.
That the bash app is kind of an artificial user and construct.
So, yeah, it's a sort of very front end construct. Like it's right on the front end, and then this remote bash executor runs deep inside the task on the execution end, and nothing in between really thinks about bash apps. Okay, so look, I even put it in bold. Executors have no idea that they're running a bash app, right? So it'll go into work queue, and all work queue does is calls this Python function that happens to shell out. And this is the Python function here.
Okay, makes sense. Yeah, thanks.
Okay, so that's the Python task model. It's basically run this Python function, nothing else. Here's a diagram that's been in our Parsl documentation since 2017. No one will remove it. And it shows a task, which I've just told you what a task is. It's a Python function running across multiple nodes. So question, who's going to tell me what it means to invoke a Python function across multiple nodes, right? Every time this comes up since 2017, which is coming up to a decade away, there is a lot of awkwardness. And that's because there isn't really a natural interpretation of that notion. What's happening is people are overlaying their own different model of what a task is that isn't what I just said. And if you pick a different meaning for the word task, then this makes sense. Okay. So we can move into the world of MPI. And MPI, I'm going to put aside sort of Python MPI. I'm just going to talk about command line MPI. So this doesn't look like running Python functions at all. It looks like I want you to run 5 copies of this Unix process in some context with ranks and nodes and things, so it can construct an MPI communicator. And it looks like 5 process forks across five nodes, for example. Okay, and that context is traditionally prepared by, say you're using Slurm, you would use sbatch and srun together. That's going to prepare your context so that srun mostly magically runs the right number of processes, Unix processes, nothing to do with Python functions here, nothing to do with Python functions at all. It's just running a bunch of copies of a Unix process in a context where they can, when they do an MPI in it, they somehow connect to each other. And if you use that as what you mean by task, then that does look like this diagram, okay? But a task in this diagram doesn't look at all like the Python stuff I said before. So there's this sort of conflict here. And depending on how much you've thought about this, you might see it as a big conflict, you might see it as a not very important conflict. So I'm going to talk about, we've got 4 executors that have some kind of MPI support. And some of them I've paid a lot of attention to, and some I haven't paid really any attention to. So I'm just going to talk through my opinions of those executors' attempts to do MPI. When I'm criticizing what's going on here, I want to be clear, this is a criticism of the task model. It's not criticisms of the implementations or of the people who implemented those implementations. Okay. So here's the high throughput executor. It's the classic Parsl executor. We've got one node which runs the workflow and has an interchange component, and it sends tasks over to worker nodes. The worker nodes have a manager process, and then for every core, you have a worker process. And the model is roughly, it's not exactly, but roughly, you run a task that runs, that gets 1 core. And there's one worker that will run that. So here's our wrapped up Python task running on this particular worker. And if that's a bash app, then that little process there will fork out and run a Unix process that, because it's being forked inside this worker, will run inside this node. And it's a bizarrely sized 3-core machine. So it will only ever run 3 tasks, which will only ever make 3 forks. So that sort of means the load limiting of saying we're only ever going to run 3 1-core Python functions also means you're only ever going to run 3 implicitly 1-core Unix executables. What does that look like in MPI mode? So the setup is very different here. We've still got the interchange, we've still got managers and workers. But now, instead of using the manager and worker model to distribute work between nodes, we let srun do that, or MPI exec or whatever. And what happens is just on the head node of your batch job, you have some workers, and those workers are expected to call out to srun or MPI exec or something like that. Now, HTEX can't see the command line because all the worker is doing is running this Python code that happens to fork. Okay, so in order to do that, your user has to bodge in to their bash app a hook so that the worker can hook into this opaque Python function to get a srun or an MPI exec or whatever bodged into the front of your command line. Okay, because the worker HTEX can't ever see this command line in the Parsl task model. It's completely concealed. Okay, so potentially you could, for UI purposes, you could make an HTEX specific MPI app which looks like a bash app, but it puts that bodge in for you as well. Okay, and if we were just trying to do HTEX, this would be a perfectly fine thing to do, I think. And still the core of Parsl wouldn't know about bash, it wouldn't even have to know about MPI. But here's a few things that go wrong. This is just a Python app. So what if I happen to run a compute-intensive Python app, not a special MPI app, on a HTEX configured this way? Well, it's going to run here on this machine without any resource allocation. The same with bash apps, the same with any wrapping that's happening. So there's a constraint that we hope the user submits apps that only ever invoke the MPI wrapper and don't do anything else. But there's no way of enforcing that because, again, this is an opaque Python function. So it's like, here's a function, we hope it only does this, but we can't inspect it in any way. Okay, radical. That's got a much more explicit task type model. So there's a task type in there that you can submit that says run this command line. There's a task type that says run this command line on multiple MPI ranks. So it's pretty natural if you're doing that. You want to say, well, here's a bash app or an MPI app. It naturally comes to mind to say, well, I want to submit that to an actual radical pilot as a command line, not as a Python task that's going to do all this forking. When I said that executors can't see what's happening inside the task, radical pilot or the radical pilot executor tries to do that. So it looks at the function it's being given and sees that it's a big wrapped stack of stuff. And it says, oh, this crawl stack happens to look like it's come from bash app. So I'm going to unwrap it and pull out the guts. And then I'm going to run the user app code now before submission. And that will give me a command line. And then I can submit that to radical pilot, which I think is pretty horrific, but there's not a better story. So if you want to submit to radical that way, this is pretty much all you can do at the moment. What happens to any wrappers you put on? The implementation choices are either you run them on the submit side alongside that command line generator, or you throw them away. Okay, so that code is not always going to do what the user thinks they are doing. There's all the stuff that we elaborately added on at the start, and then radical somehow digs inside and pulls out the command line tool. Okay, so in that sense, radical is aware that it is running a bash app so that it can do this special processing. Flux, I know a lot less about. I looked at the source code. It looks like it just runs. If you say run this 5 times, well, it runs it on 5 workers. That kind of works if you aren't doing anything interesting in your wrappers, but it is going to run the wrappers 5 times, 1 on each node. You've also got to hope that the command line generation was deterministic, because it generates each MPI call, I think, 5 times, for example, and you hope that that gives you a call that's similar enough for them to work together. Dragon, I know even less about. All I know is that the Dragon dev said, if you tell us a coherent model, we'll implement it. And I'm like, we don't have a coherent model. And that in part motivated this talk. So some thoughts are, what if we throw away this task model, or not necessarily throw it away, but what if we approach it without having too many constraints? The first thing we have to do is accept that workflow writers, component writers want to run this stuff, which is bash apps, command lines, MPI stuff that's quite a long way from Python functions. So we've got to accept that that's a legitimate use case. We've got to accept that this stuff really is not just a Python function that you can bodge around. So those 2 bullet points look the same. But one is accepting that the use case exists, and one is accepting that the use case is different. And I'm going to say, all right, fine, I don't care about backwards compatibility. We can throw away features that people aren't really using. One of the goals is I want to embrace the diversity of what executors can do, rather than end up with a really low power, lowest common denominator. The previous slides show some motivation, some stuff to avoid, some goals. There's probably other stuff going on. So I've got a few options. Option 1, the null hypothesis. We don't do anything. We leave things as they are. It's extremely low effort because we don't have to do anything. It's very high cognitive load for users, and people trying to support them. If you're trying to do, well, you've got to have 4 sets of documentation now. It's not easy to move tasks between executors. It's pretty incoherent between the executors, and also with respect to other features. All the stuff that's done in wrapping looks messy here. Another option is to tell people to stop trying to do MPI. So Parsl is for running Python functions and simple bash commands. You can't just imagine up a new kind of task in your imagination and be like, oh, I'll put a bullet point on my slide and now Parsl can run it. It's a lot tidier than the status quo. Downsides are it involves telling a lot of people to go away, and then those people won't go away, and out of guilt, we will still try and support them. So there's some technical options now. Okay, the first technical option is we don't submit this function, this big blob in red anymore. We replace that with some data structure that says, all right, I want to run a command line, or I want to run an MPI executable. So that looks a lot more like the radical task submission interface. So then the executors can see these tasks themselves. It will benefit most executors. If you look at, for example, work queue often fires up a Python process in order to then run a fork command. It could just not do that in this model. It could run the command directly. It gives you some ability to say, actually, I don't know how to run this task type, and I can raise an error legitimately rather than strange things happening when you run the Python code. The big downside here is you lose all your wrappers because there's no Python in your task anymore if you're doing command line stuff. So that's not too bad. It sounded horrible when I first thought about it, but what do we lose? In task file staging, nobody really does that. Resource monitoring is kind of limited per executor. So this doesn't mean you can't do resource monitoring. It just means each executor has to think about how to do it itself. There is some desire for bash apps that also run some Python before and afterwards. Logan has a nice feature request open for that. And you couldn't do that as a wrapper anymore. You would have to do that as a little mini sub workflow, for example. And the implementation would look like somewhere in that stack of rewriting I showed earlier, there would be a step that takes the function, args, whatever, and turns it into some kind of task description object. And then the other option, when I said, what's this nonsense question? What does it mean to run wrapped Python code on end nodes? Is to say, well, let's give that a meaning. Perhaps it means we're going to run Python just on the first rank, and then that Python can say, actually, I want to go out and do some kind of MPI equivalent API call to run stuff on the other ranks. Okay, that looks a little bit like the htext bodge, where we bodge in it an srun call into the user's command line. And this would be more formalizing in a bit. What that needs, though, at least is a per executor understanding of that call to be able to say, all right, I'm running this Python code now, you want to run on all the other ranks. I think Flux would support that the best. htext, sort of, it's not really set up for running Python on the first rank of an allocation at the moment.
Could you dive into that more? Sorry if you were about to.
Yeah, go on. Ask again.
Could you go into what you mean by cannot easily run Python on first rank? And here by rank, do you mean the first
I mean an
name?
MPI rank. So if we come back here, all the Python code as it's implemented now runs here on this sort of quasi submit node, right? So if I want to, I can run some Python here that happens to then run a command line over here, right? But if there's resource intensive Python, that resource intensive Python runs here. Oops.
Yadu would like to say something.
Yeah, yeah.
Logan, the deal is that in the MPI mode, you basically have a bunch of workers running on the lead node of the batch job. So
Mhm.
the Python code is not running in any distributed fashion, right?
Yeah, the Python code doesn't run in your cluster. It runs on this
It's
sort of
just
fake
running on
head node.
code.
Runs on like a fake head node.
Totally. Yeah, I'm
Right.
aware of that. And if we're doing so, I don't want to get into implementation details. I don't see that as
You
a
have already, though.
showstopper. Yeah, I know. I just want to make sure I understood that, yeah, cannot easily run Python on first rank. You're saying not that,
Not that you can't run Python. I'm saying you do run Python, but
yeah,
the way that HTEX is implemented right now, it is not set up to run Python in that location. Right.
then where is it? Then where is it running under?
It runs it on this fake head node.
Yeah, and that's different than rank. And by first rank, are we talking 0 indexed?
It will always run on effectively the 0 index of the batch job.
Okay, so when
Not
you
the
mean
0
first rank,
index of what, not the 0 index of, like in this diagram, like we've
yeah,
got 4 nodes. It will always run on this node, even if you're trying to run on these 2 nodes.
okay, then we share the same picture. The wording I'm still wrapping my head around, but I know what you mean.
Yeah.
So I feel satisfied.
Yeah.
Hey,
Okay.
Ben, can I ask a question about scope here?
Yeah.
I mean, I really like the direction you're going. I think it makes a lot of sense to strongly type the tasks from top to bottom because it just
Yeah.
makes it easier for everybody to match up. I like the idea. Is the appetite here to run? I'm sorry, prefixing this with the observation that machines only get fatter and fatter and fatter.
Yeah.
Is the focus here on running MPI applications that span multiple physical machines? Or is there an appetite to run moderate numbers of MPI jobs that fit on one physical machine and therefore could be managed by a single worker at a time?
So Yadu has missed the MPI use cases for Parsl. So
Okay.
he's in a better position to say.
Yeah. So Doug, I think for the MPI mode approach that we've looked at so far, the idea has always been that you are running on a single executor that spans multiple batch jobs on the same node, on the same machine. Like there is nothing that spans multiple machines. It's always on the same machine. But again, the MPI task that you launch cannot span multiple jobs anyway. So you are again limited to slicing the resources available within a single batch job into arbitrary shapes. So you could potentially do something like 10 nodes, I want 2 nodes, I want 4 nodes from that.
Let
We
me
didn't get
ask
what you
it a
said,
different
Ben.
way. Let me
You
ask a
mean
different way.
multiple nodes implicitly there, though, right, Yadi?
Sorry?
Yes.
You mean I am allocating a batch job of 100 nodes, not I am allocating a batch job of 1 node which has 100 cores.
Correct.
Yes.
Doug's
You want to
turn.
run a small number of very large MPI jobs?
Yes.
Okay.
Yes.
Okay. That's the answer to my scope of question.
Potentially sharing the same batch job. That's the deal. Because you don't want to go to the queue and ask for multiple jobs.
Right.
I got it.
Anyway, let me finish this presentation. There's only one more slide. Okay. Dragon, I don't know about. I was saying how you would implement this if you could. The overhead is there's Python in every first task now, and certainly from work queue under really heavy load, that's been very expensive. And work queue and task find have done nice stuff to try and eliminate that. So those are the two sort of technical. I'm not saying these are options that we have to pursue. It's just throwing ideas around. The outlook is fine. This is just to have ideas about where we might go in the middle long term. Default is null hypothesis. These options are just things I just made up and didn't prototype. From our manpower side, we don't have a Parsl MPI tech sponsor who's there to coordinate cross-executor behavior. I think we've only had one user that's tried to use 2 different executor implementations. It's Chris Harrop at NOAA. but people seem interested in this, right? And an important thing is this is not a trivial effort, right? We've done the hackouts and code stage. We've got all that experience. We've done it 4 times, or people have done it 4 times. So we can learn from that, but this isn't just a grab some student, give them a 6-week summer project kind of project. But we do have core team funding for doing plugging interfaces if we wanted to spend it on this kind of stuff rather than on some of the other plugin interfaces. And that's the end. So any more questions or discussion or comments? Go ahead.
So it seems like 3 people or 2 people have already suggested, and I had one of my lists of comments to be, is there anything wrong with annotating our tasks with their type and passing them into the work flow? It sounds like that, if I recall correctly.
That's sort of what would happen, right? In this first model, this one. That's effectively what you'd be doing. You'd be saying, this is a MPI task, but also here's how you get the command line for the MPI task.
Yeah, and if we're already, it's from a user side, we're already forcing people to annotate a task based on its type.
Yeah, a user will always have to do that.
Yeah, so it's weird that our implementation kind of throws out.
Yeah, you're always going to have to say, I want to run this in some way or other. I want to run 5 copies of this task. Like, that's the thing. You don't go to bash and type ls and expect it to run 1,000 copies of ls, even though you're logged into a supercomputer. Right? Something happens, some annotation happens to say, I want to run this thing 1,000 times.
But Ben, I'd be interested just in, even without major surgery, having a spec that says, here's an MPI task and here's how many ranks and what else needs to happen.
Yeah.
Would be useful to have, because it would not be a large jump for us to say, oh, you asked for a 16 rank MPI task. Oh, we can toss that on one worker. No problem. Done.
Right.
But now you come back and ask for 1,024 rank, then the executor can come back and say, you know what, I don't do that.
Right.
Well,
Yeah.
because they don't have a big enough machine.
Yeah.
or doesn't know how to split. But at least that's concrete information. We can come back and say no in a reasonable way.
Yeah.
Rather than just having mysterious behavior.
Yeah. So that size stuff actually is not too badly handled by this existing resource specification stuff at the moment, because you get these what are they called, Yadi? Tell me the fields you implemented.
Yeah, it's num tasks, task per node, and launcher options where you can pass in arbitrary options. And I think there is also a num nodes, so which would specify like the total number of nodes that you want the MPI ranks to go over, the total number of ranks, and also like if you want, you could also just specify the ranks per node. So
we based it primarily on Balsam, so we took a lot of that code from Balsam, which is why we ended up with those words, and we know that there's different terms used in the other executors, so there's definitely an opportunity to try and
the same sort of verbs used by SRun as well, so it's like familiar, people understand it.
So that bit in that sense, that bit is already declarative. Like we say, I want 10 nodes. I'm not going to tell you how to give me the 10 nodes. That's up to you. So that bit exists, I think, without really needing any change, or not any deep change.
This is at the moment. Go ahead, Pete.
This is Pete Menegral. Just a comment, at least from the Dragon perspective. I'll second what was it, Doug or whoever just said on the specification. I think that was really what we were getting at, is that there was just kind of some kind of API specification on that. The rest we can kind of implement underneath. And I'll also add as well, like that the notion of strongly annotating the function types, be it a function, a Unix process. We would prefer too that there be an annotation specifically for MPI separate from just a Unix process, so that it's, because you might want to run like many copies of a serial executable, right? But this is many copies of a serial executable that need to be aware of each other, so there's an extra constraint on launching them. But other than that, I think just having the specification would be super helpful.